Hello. I'm assuming I'm live now, so if you can hear me, just please say something in the chat. Thank you so much. All right. So today, I was going to unpack and look at a few trigonometric expressions and equations and see how we solve them. It's a very interesting part of trigonometry. It's probably the one that combines all of the things that we've been doing thus far and looking at a few things that we did in level 2. So, hi Jason, this is fantastic. Let's go. All right, so I'm hoping this is working. Perfect. All right, so let's start off by outlining a few things. We have a trig equation, that we've had the other day. It could be something like y equals sine of x. Thank you, Dr. Hoffman. Y equals sine of x. Yes, we have the A, B, C, D. They could all change and we'd have a different equation. But let's start with something very small and something very simple. Okay, suppose this equation, I wanted to find out x if y was equal to 0. Well, according to what we've done thus far, you'd go sine of x is equal to 0, and just like normal, you'd go, well, take the sine inverse of 0, type that into your calculator, and you will get x equals 0. And you're like, oh, okay, cool, that's my solution. Okay, what about another question? What if I said, find x if y is 1? Similarly, we could do sine of x is equal to 1, and then take the sine inverse, and we get, well, what's a sine inverse of 1? If you type it into your calculator, you will get a decimal, but I'm going to tell you that that decimal is pi on 2. Okay, I'd rather not use the decimal. So this is all well and good. This is how trig functions work for now. We get one solution. That makes sense. That's how equations work. We're good. However, this angle that we're working out, these angles, they're not unique. Because if I said, let's find out what sine of 2 pi was on my calculator, it will give me 0. And if I tried sine of 4 pi on my calculator, it will also give me 0. And just like before, if I did sine of 0, it also gives me 0. You think my microphone is squeaking? It might be my microphone squeaking or the fact that I have cicadas outside. Not cicadas, crickets. Tell me if you can't hear me clearly, please. There's just a lot of crickets outside. So in this indication here, are we to imply that 0 equals 2 pi? And those of you who have experienced scholarship calculus with me, this might start startling you. Does it mean that 0 equals 2 pi? No. It doesn't mean that 0 equals 2 pi. Is it okay? I don't think, oh no. Okay. I don't think I can do anything about it now, but hopefully it improves. I'm going to try for another 5 minutes, and if it doesn't improve, I'll start the stream again. I don't know if I can. Sorry guys, I haven't done anything different. Just quickly check my stream settings. I think everything is the same. If you still have an issue in a few minutes, let me know, and then I'll change my stream settings. Okay. Okay, so going back to this, 0 does not equal pi on 2. That's, but what it is when we have angles, an angle of 0 radians and an angle of 2 pi radians and an angle of 4 pi radians, they're all the same. And so that's the crux that we need to take from here. That they are not equal, but 2 pi is equivalent to 0, which is equivalent to 4 pi, which is a little bit of a weird idea. Yeah, okay, so sorry about bugs. Welcome to, it's a plague in some way, right? Okay, so they're equivalent. And so what I'm going to do is I'm going to shift from here, and I want to try and visualize what these look like. Because I think that an equation like this doesn't only have one solution, but has lots of solutions. And I want to look at how. And I want you to think back to systems of equations and how we classified sets of solutions. We said there's either one solution, which was unique, infinite solutions, or no solutions for that kind of system. And in this kind of system, we're pretty clear in the same way. There's either one solution in some kind of equations, or there's infinite solutions. And we'll talk about that. So what I want to do is I want to jump to a picture. I would jump to Desmos, but just in case it doesn't stream well, I've taken a screenshot of it. Okay, here we go. The hope is this works. Okay, cool. So if I have a sine curve, do you notice that it starts down the bottom and is periodic? Okay. And so it repeats every 2 pi. And that is really, really useful. 2 pi becomes a very important factor because it's the period. And I'm going to generalize on this one, and then we'll talk about the other kinds, okay? But sine is periodic on 2 pi. And so if something happens in this interval, then it will happen in the next interval and the next interval, and so on and so forth. Okay, so let's quickly have a look. This is the function y equals sine x. Underneath here, I've drawn y equals sine x in red. And I've drawn in blue y equals. And this was the first solution that we got, pi on 2 from before. However, let's have a look. There's another solution here at 5 pi on 2. There's another solution back here at negative 3 pi on 2. So, in fact, I have an infinite set of solutions, and they happen every pi on 2. So let's just, not every pi on 2, every 2 pi. Let's try that. If we go pi on 2, and I add 2 pi, that's the same as going pi on 2 plus 4 pi on 2, which is equal to 5 pi on 2. Similarly, if I go pi on 2, take away 2 pi, that is, what was that? Take away 2 pi, that's pi on 2, take away 4 pi on 2, which is equal to negative 3 pi on 2, which is the two solutions that I had before. So in fact, if I add 2 pi to any solution, I will get another solution if the period is still 2. Now that's really cool. Okay. Is that the only one? Well, let's try another one. Okay, let's just quickly look. And here, if you're curious, my red equation is y equals sine x once again. I didn't want to be too adventurous. And my blue equation is y equals 0.5. And so if I solved sine x equals 0.5 and solved for x, I would get sine inverse of 0.5 and sine inverse of 0.5. You should know this one, but I'm going to tell you anyway, is pi on 6. And so this first solution happens at pi on 6. I'm hoping you can see the graphs clearly. If not, tell me to zoom in and I'll try zoom in. Okay, so this first solution happens in pi on 6. Now, I'll add 2 pi. So if I add 2 pi to this number, over here, this is pi on 6 plus 2 pi. I can't be bothered simplifying that, but do you notice, do you notice that that's exactly where that dot turns up? But there's something wrong. We've got a solution in between them that we've not actually looked at. How is it the case that we've just added 2 pi and not got a solution? That's between them. The thing here is, in every 2 pi, instead of there being one solution, now there's 2 solutions. And that's interesting. And we're going to see how they relate. And on your calculator, you only got pi on 6. What's the other solution? Think about it. And I'm going to just sort of raise a few things so that we can just quickly look at it, okay? Okay. First off, we had our first solution at pi on 6. We had our next solution at 2 pi. At 2 pi plus pi on 6. Sorry guys, my eraser's not working. Okay, let's try that again. 2 pi plus pi on 6. There we go. Right? Now we're saying that there is a solution in the middle. And I just want to have a look. I'm going to zoom in. Let's have a look at this distance here. That distance there in purple is pi on 6 from this axis. But it looks really familiar because this distance here is also pi on 6. But it's from this line here. And then if you look again, once again, it's pi on 6 from 2 pi. If you look here, it's pi on 6 behind 3 pi. And so I'm going to just try and write out a whole set of solutions and see if we can make a pattern. Right, here we go. So the first solution we'll start with is pi on 6. Yeah, I'm going to just rewrite this as pi on 6 with a bit of space. The next solution that we looked at, pi minus pi on 6. That's this one here. And then the next solution is 2 pi plus pi on 6. That's this one here. And then the next solution is 3 pi minus pi on 6. Now, does anyone sort of see a pattern? Do you notice that I've just got 1 pi, 2 pi, 0 pi, and I'm alternating between plussing and minusing pi on 6? Yeah, so this is how we find the infinite set of solutions for pi, for the angle x. There's an infinite set of solutions. You could simplify these all out. You could write this as just pi on 6. You could write this as 5 pi on 6. You could write this as 13 pi on 6. You can write this as 17 pi on 6, if you so wanted to. However, what's really interesting is this structure here. Because that structure there sort of indicates to you that, hey, there's a pattern to this. And so we're going to try and form a general solution. Okay? Our general solution is going to be that if you have an equation then theta, if we let y be something, then the first solution that you get, the sine inverse of y, I'm going to call alpha. And we're going to call this alpha the particular solution. Okay, it's a solution that we're looking at the moment. It's the first solution. It's what we get out of a calculator. And often it's the one closest to the y-axis. But sometimes it's not, but often it is. And sometimes you'll get a negative one, and sometimes you'll get a positive one. It really depends on how your calculator is working that day. But I'm going to call that a particular solution, and that's alpha, right? And then we'll look at how we get the next few solutions from the alpha. Well, the first one was, once again, 0 pi plus alpha. Then it was 1 pi minus alpha. So this alpha could be anything. I've just had pi on 6. 2 pi plus alpha. 3 pi minus alpha. And so it follows this pattern. Does the internal require us to show that there is a pattern? You have to know that there is a periodic nature to the solutions. I'm not sure what our internal currently looks like, but when we get there, we'll have a chat. And so what I'm going to say is our general solution for sine looks like theta equals n pi, meaning some number of pi, plus, and this part here is an alternator, -1 to the power of n. When n is an even number, this is positive. When n is an odd number, this is negative, times our alpha. Theta equals n pi plus negative 1 to the power of n times alpha. If n is odd, then this becomes an odd number, and this becomes a negative. Okay, this is the sine general solution. Okay, it's possibly the most complicated general solution that we have in trigonometry. That's why I started with that first. Okay, knowing that there's an alternator in it, okay, and depending what n is. And so what's also really important to note is where n is any integer. Any integer n will satisfy the value of theta. Any integer, right? But some integers n are more important to us than others. But any integer n will work. It doesn't matter if n is 1, 0, 17, 443.2. Oh, it does, because you can't have decimals. But n must be any integer. Negative 8,000. Positive 5 million. Fully legit. We good. Okay, so this is the general solution for sine. Shall we look at what cosine looks like? I'm just going to leave this here for you to just peruse. Yes, exactly. And that's why, Yun Chen, well done. That's why I showed you this one first. Okay, because the distance, I did in purple, from 0 pi to 1 pi is the same. And this is your alpha, and it doesn't matter. It's going to be the same. And so both of those points sort of become the same point. And so that's why you don't have to worry about the alternating. Okay? Because 0 plus alpha and pi minus alpha is the same number, in which case it's the peak. Right? Remembering that we're working on the assumption that 2 pi is the period. Okay? And so therein you can see that I'm about to have a conversation about what the period will have to do with this. Okay? And I want us to come back to this equation here, because you can transform this equation just a little bit using what happens when the period is not 2 pi. And you can pretty much plug in half the period here, and you will get the right general solution. As long as this particular solution is correct. And I'll talk to you about that later on. That shouldn't be the focus of our discussion right now. Okay? All right. So let's go have a look at what happens to cosine. Thank you, Yuan Chen. That was an excellent question. Okay. Cosine is very similar to sine. It's got the same curve. And so let's see what happens. Well, when you do a solution, I don't know, if you do, say, cosine of x, y equals cosine of x, and the blue one is y equals 1, the same as we have cos of x equals 1, cos inverse, that's really good. My whiteboard just went. I'm going to try and get it back really quickly. Otherwise, we will quickly just switch to Desmos. I don't know what happened to my whiteboard. Okay, perfect. So we'll look at cosine. So on cosine, if I used the first one, cosine, I'll just quickly change this and this. Try to get the whiteboard back in a second. But if I quickly have a look, the first solution happens here, and once again it happens after 2 pi. So that makes sense. When cosine of x is equal to 1, it happens every 2 pi. Similar to how we did before. Okay, now though, what about if cosine, instead of equaling 1, it was equal to 0.5? Once again, I have one solution, and then if I go 2 pi on that, I get another solution. So the difference between the solutions is once again 2 pi. However, there is a solution in the middle. The solution in the middle this time is not the same kind of symmetric as before. We've got to figure out how this solution comes into play. I'm thinking my whiteboard's almost back up and running, so I'll probably switch to there. But do you notice that within 2 pi, so from this peak to this peak, I have two solutions? And can you notice that there's a line of symmetry through pi? And so that symmetry is going to be really useful. There's also a line of symmetry through 0 and through 2 pi. And in fact, every multiple of 2 pi, there is symmetry. And so for every multiple of 2 pi, there's symmetry. And so that's what we're going to use to carry on and write our statements. Okay, so fortunately, my computer has decided to continue working. And so I'm going to switch back to my my document I had before. Sorry, guys. So just give me 1 second. Okay, so x was equal to 0. That shouldn't have been a surprise. And so if we went down, we noticed that when y was equal to cosine of x, and y was also equal to 0.5. Sorry, that was meant to be blue. We got cosine of x equals 0.5, and x was equal to, what was our solution? Well, cos of x is equal to 0.5. The cos inverse of 0.5 is pi on 3. So that was our first solution. So that's this one here. So if this is pi on 3, what's the one here? And given that we've got the symmetry in the y, this must be negative pi on 3. And if we go up to 2 pi, it's the same distance from there, the same distance there, same distance there, same distance there. So if I wrote out my solutions, sorry guys, I can't see if you can hear me. Just check. So please just let me know if you can hear me. So my first solution was pi on 3. My next solution, I went back and I got negative pi on 3. And then my next solution is going to be 2 pi minus pi on 3. And my next solution is going to be 2 pi plus pi on 3. And in fact, I'm just going to write 0 pi And then I'm going to write 3 pi. Is it 3 pi? No, it's not. It's actually 4 pi. And we start with minus. It's 4 pi plus pi on 3. And so if you can sort of see, this once again is alternating. But in this case, this is going up every 2. It's only even numbers. And so since it's only even numbers, if we had a general case, y equals cosine of theta, then cos inverse of y, we'd still call our alpha, which is our particular solution. Okay, and this time our general solution is in the form, okay, not geo, our general solution is really nice. Theta is equal to 2n pi, so an even number times pi, and it's plus or minus whatever that alpha is. Once again, it's really important to note where is any integer. All right, so this is how we get the general solution for cosine. So whatever the first particular solution is, sometimes people call it the principal value. I'm just going to use particular solution and general solution because that's what I used in systems of equations, but people might use the word principal value. But we'll see how this changes over time. There's some pretty cool stuff that I might do in another video to explain that. But once again, I just want you to relate the period of what's going on. Do you notice that you see 2 pi in this? You know, and that's why some people might like to write this as 2 pi times n, okay? Because it's a multiple of yes, we've not used it in the past. We could, yeah, that's a conversation for discussion, Harry. Dr. Hoffman's right. It would make a lot of things easier for you, but we'd really want to see what you can understand. So we're working on it, and yeah, we'll see how things go. So I still want you to recognize the relationship between 2 pi and the period of this function, because there's some cool intricacies that we can come to later on. Okay, that's the cosine general solution. And so I'm going to do, hopefully my tan one won't take as long, because I think we've got the main idea right now. So let's shift over and see what we get in tan. Oops. A tan function. Notice I've just changed this axis. It is only periodic on pi. And in fact, any solution I get only happens once in any period, not 2 times like we've had before, because there's an asymptote and there's just only one place you can cross a tan with a horizontal line. So let's have a look. Once again, we've got the red equation is tan x, and the blue equation is 1 equals, good God. Sorry, team. Go back to where we were. Don't know how that happened. I don't know, these computers are freaking out on me today. Cool. This is great. So tan of x, and the blue is y equals 1. And so then tan of x equals 1. And so x is equal to tan inverse of 1, which is pi on 4. And you notice that, this pi on 4 situation repeats every pi, and that's all it is. There's no two ways about it. And so if we let our general equation be tan and then have tan inverse of y be equal to some alpha for our particular solution, right? If we take that to be our particular solution, then our general solution I'm very confused as to what's happening with my pen. Sorry guys, just give me a second. I don't know what's happened to the buffer as well. Our general solution for tan looks like this. Theta equals n pi plus, where n is any integer. Okay, real simple, nothing too crazy. And this is the tangent general solution. Okay, and that's what they look like. They all look like this. And so as a whole, you have the tangent general solution, the sine general solution looks like, the sine one is the only one that's really weird. It is n plus -1 to the n alpha. Cosine is 2n 2n pi, or 2 pi n plus or minus alpha. And the tangent solution is the simple n pi plus alpha. Ooh, that's not pretty. N pi plus alpha. Are they all excellent question? I know sine, but I know sine is. No, these are not necessarily excellence ideas. This is still something I'd still consider being around merit, because knowing that there's general solutions, you can try to find multiple sets of solutions. I don't really want to spend too much time on whether they're merit, excellence, or whatever. I'd rather focus on the ideas behind them and how we can apply these. So now that if you solve a trigonometry expression, you can now not only give me one solution, but you can give me a whole swathe of solutions. I've noticed that I'm near 40 minutes, and so I'm going to just quickly do 2 examples and I'm going to wrap it up, okay? So, examples. Give the general solution for the following. Ooh. Okay, so first question. Sine of x is equal to 0.4. Okay, so I'm going to use decimals in this. When will we need to find out when two trig graphs are equal to each other? That will be a little bit later. There's a few more nuances that I want to cover before we get to that. I just want you to understand that we've got general solutions. Yeah. Oliver, I like your question. I think your question has a very poignant point. That's when our identities and stuff get intertwined to what we're doing with this. Because do you notice how this is quite distinct from what we're doing with our identities? And so we will have that conversation in the coming weeks. Don't stress too much. We might leave it for a little bit. We'll probably look at seeing what we can do next week. Okay, so I'll solve this. So first off, is equal to sine inverse of 0.4. And whatever answer I get here, I'm going to get some terrible decimal, but I've picked some number that I know ain't going to be pretty. So sine inverse of 0.4 is 0.412 to 3 decimal places. Okay? And I'm going to take this and I'm going to call this my alpha. This is my principal solution. And so all I need to now do is go, well, x equals, look at the sine general solution, n pi -1 to the n of alpha, and in this case, alpha is 0.412, where n is ne and 2. And I'm done. That's not actually that hard, is it? Now, you have to solve things that slightly look more difficult, and that's when this part here starts to look a bit funky. But the algebra is the same. So I'm going to do one more where it's a bit crazy, and I'm only going to deal with I might do a cosine actually. Yeah. So we're going to go 2 cos I'm going to just go pi x minus 1 equals 1. How about that? Okay. Looks a lot crazier, but we'll do it. So first off, I'm going to divide by 2. Okay. Then I'm going to take the cosine inverse. And if you recall, the cos inverse of half is pi on 3. And this time, I'm not looking at my x. I'm not solving for x yet. Typically, what you do is at this point try to solve for x, but I'm going to say that this is my principal solution, or my particular solution. This is my alpha in this situation, and this is my theta. Well, maybe I shouldn't put over theta because some of you are confused. So that is my theta. That's my alpha and that's my theta. So I'm going to write it out. And the cosine general solution is theta equals 2n pi plus minus alpha. And so I'm going to substitute those in and see what happens. Theta well, theta in this situation is not theta. Pi x minus 1 is equal to 2n pi plus pi on 3. Okay? You're like, okay, let's go. What do we do now? I'm going to notice that there's a pi on all of them. I'm going to divide through by pi. And so I will have x minus 1 is equal to 2n plus or minus 1/3. And then now I'm going to add 1. I'm going to add 1 to the front here. Still a plus or minus 1/3. Where n is ne. And this is my solution. And I could list out a whole bunch, and I will. Just watch. So I'll be x equals and I've just separated the plus and minus. And I'm going to just plug in different n's and we'll see what happens. So this is n equals 0. Actually, just humor me for a second. I'm going to put the minus here and the plus here. Okay, n equals 0, I get x equals 0, 1 minus 1/3. So this is, I'm going to just write 1 minus 1/3. And then x equals 1 plus 1/3. And then n equals 1. N equals 1. So 1 times 2 is 2, plus 1 is 3. So I get 3 minus 1/3. And the same thing happens here. I get 3 plus 1/3. And you notice that I could probably list out a whole bunch of solutions. So will we need to show how the general solution, to get the general solution? The algebra? Yes, you probably will. But let's not focus on the internal, because we're probably not doing the internal for a little while yet. I'd rather just focus on the algebra. Okay? I think this might be an interesting point to stop the video, because I think we've covered general solutions. I think we've covered a lot of ideas. And plus I've got 10 minutes to get ready for my next live stream. But talk to your teachers about what we've learned in this session, and we will hopefully unpack this idea next week. I may or may not do live sessions next week. Why didn't you divide by pi initially? I didn't divide by, so Oliver, if you're asking why I divide by pi here, it's because if I divided by pi, it'd still be okay, but my general solution wouldn't be correct. Remembering this whole thing has to be my theta, and this whole thing is my alpha. Okay? And so that's why you don't divide by pi in that state. You take that as your theta, and you take this as your alpha. And you've got to go from there. Okay? Because if I divided by pi, then my general solution would look wrong. Because and then I've got an extra pi in here, and that's wrong. And that's not what I want. But if you notice something curious, you might have decided that actually the period is 2. And so we'll have that chat later, because there's a slightly more pretty way of writing the general solutions, but we'll have that chat once we're a little bit more familiar with the algebra of what we're doing here. Okay? Thank you so much, team. Ta-ra, and I'll talk to you next time. Bye for now.